Hey, welcome everyone. So this is the third session of our Coffee O'clock, where we host researchers who actually working on quantum computing, and then where these researchers they try and give introduction to their field. Of course, Akash will be going into all that, but right now I think I'll just give a short introduction to what Q India is and what we are trying to do. So as Q India, we mostly international students or people from all over the world who are interested in quantum but have roots in India and want to do something or want to develop a good quantum community in India, right? Because there's a lot of potential, there's a lot of talent, like I said, in all of these programs, right? Today in the One Quantum India event, the person, the the main person who was giving the speech, he was from IBM, and he said that this IBM summer school that this happened. Uh, Within 15 minutes, the 2000 registrations or the 2000 spots got filled up, and he said that 70% of them were from India. Right? And that's enormous. That's the
Seven
amount of
7 minutes. He was giving wrong statements. Not 15 minutes. 7 minutes.
That's more
right. Maybe he was just like, yeah, 5 minutes or 15 minutes. But anyway, the point is, it just got over, and so many of them were from India, right? So there's a huge amount of interest. There's a lot of potential. There's a lot of talent in India, and now having something like a community will definitely be helpful for this cause. And that's what we as Q India is trying to do. So we are a voluntary group, and it's basically just people interested in quantum trying to help other people interested in quantum. And we learn and we grow, and all the usual network effect kicks in. Right. So with that, I hand over to Akash Kuttu, who will be taking us through the talk.
Yeah, thanks, Rishi, and welcome everyone. So this is the third session of Coffee O'clock by bi-weekly meetings. So here we usually, for the first half an hour, there is some person like some guest who speaks about some particular topic in quantum physics, either it's practical or theoretical, or like experimental. And then the remaining time we do a casual discussion on the topic of the talk. So today we have, and I'm your host, Akash Kundu, and I'm a PhD student of Institute of Theoretical and Applied Informatics, Police Academy of Science. And today we have Aritra Sarkar as our guest speaker, and he's going to speak about an interdisciplinary, he's going to give us an introduction on quantum computing in an interdisciplinary manner. And it is going to be very interesting because Aritra has his career is from his bachelor's to his PhD, he is like an interdisciplinary person because he did his BTech from Indian Institute of Space Science and Technology in avionics. And then he did his master's from TU Delft in quantum computing, quantum computer experiments, I guess. And then he did his master's thesis on quantum algorithm for genome sequencing, which is indeed very interesting. And now he is a third year PhD student in QuTech, and he is working in an intersection of quantum information and quantum computing. So we are very much happy to have Aritra as our guest speaker. And Aritra, the stage is all yours. Please proceed.
Thank you, Akash, for that lovely introduction. Yes, so let me just share my screen while we begin, and that normally doesn't work for me the first time.
Looks fancy.
Yeah, so which screen do you see? The slide notes?
We see a black screen now.
Yeah.
Awesome. That's what I want you to see.
Okay.
Yeah, so before I begin the talk, if any of you got intimidated by the comment from Rishi in the post that the theorists would strike back today, so that's like an inside joke that theorists and experimentalists don't go well together. Yeah, but normally they don't kill each other when we see each other. That's partly because we never see each other. Theorists never go to the lab and the experimentalists never come out of their lab. So yeah, so no like theorists or experimentalists were harmed so far. But like, as we'll see in this talk, that we will have to kind of work together if we really have to build a good quantum computer. Right. Yeah. So in today's talk, I'll like go all over different topics from philosophy, economics, quantum computing, quantum mechanics, and mostly computer science a lot. So that will be more like a broad overview, not specifically of quantum computing, but of the field of computing in general. So these are the things that I think we should keep in mind as as quantum computer and the research on quantum computation progresses over these years. And I'll start off with almost a story from 2.5 millennia back, what's called as the Cave of Plato. So Plato was a Greek philosopher, and he imagined the situation where a person was chained to the wall. So this guy over here, and he is looking at the screen at the shadow of a bird that's being like projected on the screen. Right? And while this is something like a lot of debates on this has happened on this like scenario over the years, it kind of shows that there are two phases of reality: the ones that we see in front of us, like that we can sense, and the other one is what's actually what we call as reality, what's actually happening outside the world. And we are kind of prisoners to our senses. We cannot go past a limit where we can just stand up and actually see what's going on behind the prison or the cave in this case. So we'll come back to this allegory of the cave of Plato later on, but that's one of the core themes of today's talk, that there are kind of two realities: the one that we can sense and the one that's actually happening in the world. So with that, let me start. I'm Aritra Sarkar, and in today's Coffee O'Clock session, I'll be mostly talking about quantum computation. We'll move from classical computation in general to the past, the future, and what's actually happening in quantum nowadays. So let's start with some very general question, that what is science? And I'm assuming most of you who are over here is in some way or the other from the field of science, related to some field of science. But you need not be from the scientific field to understand what exactly is science, because even babies do it. So we normally make an observation in science, then we form a hypothesis of what that object is. Then we perform an experiment on that hypothesis. Based on that hypothesis, we analyze the data and we report our findings, sometimes very noisily to the entire world based on how good it is. And once we are happy with the results, or we invite others to try out the same thing. So this is the basis of the scientific method. And even a baby knows how to do that. So in this talk, we're going to focus on one specific part of this, on how to form a hypothesis and what exactly is a hypothesis. So if you look at what scientific hypothesis is, it normally has two functions. And the most important function of that is to make predictions. And that is the basis of the usefulness of the hypothesis. So once you have a hypothesis, if this baby sees this green thing again in the next time, it would know what to do with it, whether to eat it if it liked it the last time, or to not eat it if it didn't like it the last time. So that is what predictions are useful for. But if that is all, like that's the only outcome of a hypothesis, we won't be actually satisfied. That doesn't cover the entire story. A good example of that is the heliocentric and the geocentric model. In one, you have the Earth at the center. In the other one, you have the sun at the center. And both models basically works very close to each other when it comes to predictions. So you can use both of these models equally to have the predictions. One of them is a bit tough. The math is a bit tough. For other one, the math is simple. But if you look at Einstein's theories, there's no preferred reference frame. So there's officially no way, no reason to choose one over the other. So that's where the second important part of the hypothesis comes into play, and that is to make models out of our world. So the models, the main reason to make models is to explain it to other people so that the other person understands it quite nicely. Oftentimes, like even though the model is more simple or easier to explain, it doesn't turn out to be good. Like at least didn't happen for Copernicus when he tried to say that the sun is at the center. So what is easier to explain semantically is a lot different on what predisposition that person has on what the model is currently. And the second part is it should be ontologically closer. So that's a very heavy philosophical term. And ontology basically refers to reality. So what exactly is real? Am I able to model? Is my model reflective of that reality out there? So both of these terms, semantically and ontologically, are very loaded terms, and it's not easy to fix or to compare two hypotheses based on these without having a very scientific way of doing that. So in science, we normally use a different method on choosing models, and that's even a much simpler idea. So if you have two different hypotheses which are equally good, which explains which has the same predictive power, then we normally choose the one which is simpler. Okay, so again, we're just replacing two hard terms semantically and ontologically with one term, simpler. So now we have to define it. So what do I mean by simpler? So that's where Occam's razor comes into play. So that's normally the simpler model is the one with the less assumptions. And if you like math, another word for assumptions is axioms. So basically they are the same thing. So axioms are the assumptions that you have on your set of statements, and then you derive other statements based on those axioms. So this entire process of Occam's razor is a rule of thumb. That's very, very important to remember, that a simpler hypothesis does not mean that it is true. It's for most of the cases it is true, but it might be that the actual world is very complex. Okay, so this is like a cartoon from Rube Goldberg, and like he was famous for making all this contraption kind of cartoons. And this is a self-operating napkin. So in the back end, you can imagine that a napkin is getting operated by all these complex contraptions. But when you're modeling it, you might model it as something very, very simple. So what is actually happening in the reality need not be simple. It's just a rule of thumb that most scientists prefer using when they are working with science. So this is how we have been doing science since time immemorial. Like we are trying to find out a very simple model that explains all the predictions that we want to do. And one guy took it a bit further. Okay, so he tried to axiomatize all of mathematics, and that guy was Hilbert. So around the 1900s, he got too carried away by Euclid's axiomatization of geometry, and he wanted to do that for arithmetic. So when you do that for arithmetic, you normally need to take care of three important assumptions, like three important properties rather of this set of axioms that you have. And those are completeness, consistency, and decidability. What do these mean? For completeness, it means that all true statements can be proved from this set of axioms. So if you have a statement which is true, you should be able to derive it from whatever the set of axioms that you choose. Consistency means that from this set of axioms, you should not be able to reach a contradiction. So you should not be able to prove a false statement or disprove a true statement. And decidability is a bit tougher. So that normally means that you have a way of reaching the truth or the falsity of a statement. And you should be able to follow a process so that you reach, you are able to do this kind of proofs in your formalism. So he had this dream that mathematics, or specifically arithmetic, will be, we will be able to find a set of axioms that has these properties. Unfortunately, only a few years after he proposed this, a very young mathematician, Kurt Gödel, proved kind of that the world is not so easy. So these are his famous incompleteness theorems, where he says that you cannot have a complete system which is consistent and the other way around. It took another guy, Alan Turing, to prove the third one, like disprove the third one rather, that there is a possibility of undecidable statement in any set of axioms. So why it took him a bit while longer than Kurt Gödel is because when Hilbert stated this problem, the concept of algorithm was not very developed. And Alan Turing basically had to invent all of computer science to just prove this thing that Hilbert was proposing. So now let's look at how Alan Turing ended up doing it. So he proposed a specific kind of machine, a thought experiment kind of thing, which is called as the Turing machine. So the machine is very, very simple. It has this tape, an infinite tape where you can write or read zeros and ones. And then you have on the yellow part a finite state machine. I'll come to that. And then this green thing is the read head. So it can move the tape left or to the right. And then the finite state machine has a way of sensing what's written on the tape. And then it does some calculation in the finite state machine and writes back a 0 and 1. And the finite state machine looks like a transition. So that's like very similar to how your coffee machine or your washing machine works. So when you press a button, something happens and it goes to a state. And then based on that state, it starts to do some, like it gives you some output. So for each kind of algorithm, you can make a finite state machine of that. For example, over here, you can have a finite state machine basically for a traveling salesman problem. And you can have multiple machines for every process that you can think of. You can have a finite state machine for that. And for example, you can have one for multiplication, one for sorting, and so on and so forth. So you can have many different algorithms encoded in that yellow part of the finite state machine. So given this set of machines with each with its own algorithm, now instead of changing the finite state machine every time that you want to implement something, you can come up with what's called as a universal Turing machine, where instead of changing the finite state machine every time, you make a binary encoding of this transition function that you have and put it on another tape. So that can be part of the same tape, it doesn't matter. But this part of the tape is finite. So now you have a finite number of algorithms that you can put it on the tape. And the machine is going to read what's written on this tape and understand it as a program and then operate based on that. So this is the basic concept of the stored program machine that we all use right now. So when you write a Python program, for example, you write some instructions on this red tape, and then you provide your input on the blue tape. It does some calculation and gives you output again back on the blue tape. So once you have this machine, you can make another very contradictory machine, which can, let's imagine that you have an algorithm which tells you that this machine will halt or not. So whether, let's say, when you plug into a coin inside your like coffee machine, whether it's going to give you a coffee and then stop. So Turing found out that if such a machine exists in which you can predetermine, like already know in advance whether it will stop, then you can create another machine where if it halts, you go into an infinite loop. And if it doesn't halt, it doesn't halt inside the infinite loop within the machine itself. So now you kind of have a contradiction that if this machine, the inside machine halts, the outside machine doesn't halt. And if the inside machine doesn't halt, the outside machine anyway doesn't have a way of halting. So by this, he was able to kind of prove that there are undecidable things that you cannot make with an algorithm. So like basically he had to invent all of this just to prove Hilbert. But this is the model of computation that we use till this day. So once we have this machine, Turing was able to prove something else, and that's with his supervisor, I guess PhD supervisor, Alonzo Church. So this machine apparently turned out to be super powerful. So now you can take any physical process, whatever you can imagine, and then you can write an algorithm for it. So once you have an algorithm, this algorithm doesn't only work for that particular physical process, but it also works for the same physical process in a smaller or a greater scale. Imagine like I'm creating this cloud in the PowerPoint. So there's just one program that somebody has written how to make this cloud. And that same program has been called with different inputs that is generating this smaller cloud or the bigger cloud. So basically there's just one algorithm. And this bigger and smaller thing is called as the problem size. So now you have this way of expressing this physical process. So it's more like a pseudocode. And then you want to select a machine where you want to run this algorithm on. Let's take the universal Turing machine that you saw in the last slide. So I have this algorithm, the idea of what I have to do with this process, and I want to run it on a Turing machine. It turns out that Turing machine is not the only choice. A lot of different people around the same time came up with many different ways of running algorithms. And somehow they turned out to be equivalent. And what do I mean by equivalent? So when you have this algorithm and you have this a particular machine, you can write an implementation of that algorithm on a machine. So if the algorithm by itself has some complexity, that is CA, for example, just implementing it, just porting it to that device, adds some additional factors to it. So that is like for the Turing machine, it is TMA, for example. For the lambda calculus, it is LCA, and so on. So by equivalent, I mean that when you take one of these constants from some other type of machine, it seems that they are always related with a polynomial factor. So that's n to the power, n is the problem size, so n to the power of something. It can be n squared, it can be n to the power of 100, doesn't matter. But you take any implementation and you try to map it on any other implementation, you are at most offset, or you get an advantage or a disadvantage at most of a polynomial factor. So this is what computer scientists call that they are efficiently implementable on any of the machines. And this is basically the idea of universality. So this is also behind the computing revolution, starting from the earliest computers to the latest supercomputers that we have, also like the personal computers. So they are also there. So just the Turing machine, the idea of a Turing machine and all the computers can be made, you can have a polynomial factor translation between them. We went ahead into the computing revolution and were able to create so many like gadgets that that progressed our civilization. So when it comes to the classical computing revolution, the most important tool that we had was the transistor. And the transistor is basically works like a switch. It's like takes into effect the tape that we saw on the Turing machine. So it turns out to be zeros and ones. And with that, we can create what's called as a NAND gate. And the NAND gate is a negative AND. And the NAND gate is universal in classical computing. So with just the NAND gate, we can encode any algorithm or any classical logic that we can think of. So you see the truth table of a NAND gate on this slide. So if both the inputs are 1, it becomes a 0. And for all the other cases, it becomes a 1. So just with this transformation, just with this kind of mathematical Boolean function, we can encode any of classical logic. And this has been the force behind all the computing revolution. So now, while all this were happening in the classical world, something else was brewing in some other parts of science, and that's the quantum revolution. The collective IQ of this photo is too high, like most of them are Nobel laureates, I guess. So this was again in the early 1900s and around 1926, I guess this photo is from the Solvay conference. And a lot of physicists were trying to understand a new set of laws that apparently governs our reality. So they are trying to understand, is the physical reality different, like from the earlier laws that we had from Newtonian physics and from electromagnetism, for example, and thermodynamics as well. And one of the core experiments of that kind of has all the factors that made this quantum revolution very strange is the double slit experiment. So this is like the face of quantum science. You can call it the face of quantum science. So when you take a light source and shine it on like two slits, what you end up getting is an interference pattern on a screen that's kept a little bit far away. And from what we had at that time, we had the concept of classical waves with us, like water waves and mechanical waves. We also had the notion of how a particle would behave if I like shoot bullets at the screen. And it turns out that one of the easiest way for explaining this phenomena is if we use the concept of waves of what exactly happens between the slit and the screen. So it's not possible to exactly observe what's happening between the slit and the screen, because the moment we observe, every single time we would see a particle. But if we use the math or the mathematical formalism of the waves, we can get this interference pattern out on the screen. So that is important, that we are creating a model so that it is understandable to us based on what we already understand in the classical world. So with that in mind, with that formalism within our minds, people came up with the different postulates of quantum mechanics. There are many, many ways of defining the basics of quantum mechanics. And so one of them, like this is, I directly took it from Wikipedia, and there are around 6 different postulates. So if you follow these rules, you can basically describe everything that's happening in the quantum world. I won't be going into it, so don't worry about that. But the problem was that quantum mechanics was like one of the most successful theories we ever had, along with general relativity and the standard model. And it hasn't failed any tests so far as such when it comes to experimentation. But scientists are like kind of never happy. So we had this axioms that you saw in the last slide, and people started like questioning, are these axioms ad hoc? By that, I mean like whenever there's nothing that's explainable in the experiment, are we creating just a way of explaining that? And we are remaining happy with that. So that led to the question of what exactly is real. And that is what the quantum interpretations are about. And it happens to be there are a lot of different interpretations. And this is again from Wikipedia. Again, I don't want to go into that. But basically, every interpretation is about how to explain whatever is going on between the slit and the screen. So it might be that there is actually a wave and it's collapsing. It might be that the past and the futures are interacting when it comes to the screen. So that's like the two-state vector formalism and transactional interpretation. It might be that the universe is getting split into many worlds and you happen to be in one of them where it is in the value that you saw as it collapses. So there are so many different interpretations, but one of the most important thing is it is not possible to experimentally separate between them. So every time we have there is no way to choose one over the other. So just keep this interpretation aside for a while. And let's look at the things that we can test. And that comes from what's known as the Feynman approach, that one of the best ways of learning is just by doing. So Richard Feynman's around the 1980s suggested that if we have quantum systems, we should be able to model them as well. So let's have a quantum system that's interacting. Can we control it in some way that we initialize our controllable system similar to what we expect the actual system to behave. And then we evolve that system, again, very similar to what we understand of the actual system is behaving, so that like if we do this stuff, then we should be able to understand how the dynamics of that system will change over time. And we are going to get a similar kind of measurements when we do it on this system. So this is his initial idea of how to make a quantum controllable system. And instead of passively sensing what's going on, that's what people were doing so far in quantum mechanics. Can we also take charge and do something proactively? And he has a very nice book, and I would recommend it to all of you, on how that led to the idea of computation or quantum computation more specifically. So he was basically taking this idea of quantum mechanics from science to technology, where you can not only experiment passively, but you can change the face of reality and engineer and control quantum system. So as he said, like you should be able to design a system which you can control, but that led to a small problem. And that's based on what we saw earlier in the Church-Turing thesis. So in the Church-Turing thesis, we saw that if you take any process, you should be able to model it with your algorithm on a computer, and you should be able to run it. And no matter what system, like what computer model of computing you choose, you should be able to translate it in a polynomial time. So you should be able to do that. Like if that is true, note that this is a thesis, so it's not a law or an axiom. So nothing is getting broken by this process. So if you take a subset of all these physical processes, which are specifically quantum processes, and you try to do the same thing. So you make an algorithm based on what you understand how the quantum process is working. And now you make a quantum version of this machine. So you make what's called as a quantum Turing machine. And David Deutsch in the early 1900s is 1990s, sorry, is the guy who kind of worked out the math and the model of doing this. So once it works exactly the same way that Church and Turing did with the normal physical processes. So you have an implementation on a quantum computer, any of these three. And then you have a factor, which is the complexity, inherent complexity of your algorithm. And you have a factor, which is the translation overhead of running that algorithm on your machine. But the surprising problem, the roadblock came when you started comparing these type of systems with the normal computing systems that we have. So if you take now an universal Turing machine or any of the ones that you saw before, you again have like a factor, which is like the classical translation overhead and an inherent complexity of the algorithm. But now they do not relate with a polynomial factor, and that is now an exponential factor. So this is any number. So it can be like 2 to the power n. If you're working with qubits, if you're working with q traits, it's 3 to the power of n. And this 3 to the power of n factor or 2 to the power of n factor grows way, way faster than an n square or an n cube factor. So that was the problem. If you take a quantum process and try to run it on the computers that you normally have, you end up with an exponential overhead of running it. And that was one of the theoretical reasons to work with quantum computing, like to develop quantum computing models. And when people started developing these quantum computing models, the ones that you see over here, like universal Turing machine and gate-based models, they came up with exactly like in the classical case, they came up with many equivalent models. So these are known as the quantum computing models. Some of the ones that I have listed over here, like the circuit model, that's the one that's used mostly, used the most. It's based on the logic. It's kind of a translation of the Boolean logic, the NAND gates and the NOT gates and AND gates, those kind of gates into quantum. So in quantum, they are normally unitary gates. So that is known as the standard model of quantum computing because it became so popular, because I guess it's easier to understand if you already know about how the classical computers are built. But that is not the only model. There are other models like topological measurement-based quantum computing and adiabatic quantum computing. And each of them works very differently, but at the end, they are equivalent. And that is because you can take a quantum Turing machine. So that is exactly like a Turing machine, except that instead of bits on the tape, you have qubits. So they can be in a superposition or they can be entangled with each other. And then instead of a finite state machine, which might be irreversible, you have a reversible unitary process that takes in this input, transforms it, and puts it back on the tape. So this is the model of a universal quantum Turing. This is not a universal web. It's the model of a quantum Turing machine. And the fact that these models, all these four models are equivalent to each other is because you can take any algorithm and map it onto model one of these models. And then if you try to model that same algorithm on any of the other models, at most you will have a polynomial factor associated with it. So this is important that this polynomial factor anyway gets added whenever you change models, because if you expect a short type of speed up, which is an exponential speed up, you are going to retain that exponential speed up irrespective of whatever models you choose, because at most you have a polynomial overhead and you have the exponential factors of the speed up grows far faster. But if your inherent problem is a polynomial factor speed up like the Groover search, then changing models might not retain that speed up. For example, Groover search was proven to have a quadratic type of speed up on the circuit model. But if you take Groover search and try to run it on the adiabatic model, you tend to lose that speed up if you don't do some tweaking. So in the adiabatic model, searching is not so easy the same way that it is in the circuit model. Yeah, so this is the basic of quantum. I won't go into that. This is like the equation and the math that normally scares people out. But in general, it is very simple. It is just the generalization of probability to complex numbers. Why complex numbers? Why not something more complex like quaternions? Is because this works. Like that is the only thing that we need. This mathematical formalism, if we use that, it like agrees with our experiment. So that is the reason why we use this kind of complex numbers to model the quantum states. The catch with using complex numbers or like this kind of quantum superposition is, as and when the state grows, it kind of the number of terms that you need to express that state completely grows exponentially. So you very fast end up with a very high number of variables that you need to take care of to model that quantum system. So unless you're using another quantum system like the quantum Turing machine or the gate model quantum computer, you will soon be overrun, or you will be out of your memory and you won't be able to track it. But something is super important over here, that you still can do it on classical. And a lot of people forget that even though there is an exponential overhead, that doesn't stop you from doing it on classical. It's just that it is exponentially difficult in terms of either time or the amount of memory you would spend doing it. And so now that we have all this idea of quantum developed in this talk, people started taking it a bit too further, in my opinion. So earlier again, going back to the ancient Greeks, philosophers always like to imagine everything is made out of something, right? So in the early days, like for example, Thales, imagine everything is made out of water. Democritus, another like famous Greek guy, he was one of the first atomist school, and he imagined everything is made out of atoms. And then, of course, there are like more famous philosophers like Descartes, who imagine everything is made out of mind and or body. So yeah, it gets kind of philosophical. But along this line, like along this development, what we normally see, the trend is we try to imagine everything is made out of something, and that something is typically the most pure idea that we have in mind. So water, for example, was like the epitome of purity in a lot of ancient cultures. So that's why, like, for example, the idea of ether came from the idea that something is like as pure as ether. There's nothing going on in the ether in the free space. So later on, like continuing this trend forward, eventually people thought that one of the best feat of engineering that they could come up is clocks. So the Swiss is known for their clocks. And so they imagine that the universe is a clock and God is like the watchmaker, and the universe is working like a clock. So it's like a clockwork universe, famously known as that. And everything is deterministic. And this is also what Newtonian laws kind of supported, that you should be able to determine what's going to happen if you can keep track of all the variables. And eventually, like once the clockworks got more and more complicated, people started making computers. And that's where people realized that maybe computers is a better way of understanding the universe. And one of the theses from Konrad Zuse, so that translates from German as calculating space. So this was in his thesis, he said that maybe the universe is working like a computer. Of course, now we kind of imagine that we have a better form of computers. So that is the quantum computer. So of course, like there is a translation of that. So we now say that the universe is a quantum computer, and that is a book written by Seth Lloyd, one of the founders of quantum computing. So in this book, he says that basically the universe is like a quantum computer program that is evolving as the universe is progressing. So this is also the idea of how we program a quantum computer, that we try to make it work the same way that the universe is working underneath whatever we see. So let's take the double slit experiment again. So we know how we can describe the math of the double slit experiment, but now instead of putting a simple light source, let's put something that we want it to do. So that's where we want to control it, where we put in a cat image. For example, if you're doing machine learning and you want to differentiate between cat and something that is not cat, and eventually we want something like this at the end on the screen. So if you have like pointers which marks different animals, you want the light to shine on the cat with the highest intensity. So that is basically the idea of quantum computing from quantum mechanics. So this is how the experiments would look like in a very, very abstract level. So this is also how most quantum algorithms work, particularly in the gate model, because that's the one that I have over here. So you start with some state, you create an entire equal superposition of it. Then you encode your classical input. So that's where you encode the cat image inside your state. And then you do some kind of clever process that is the quantum algorithm. You measure it out, and finally what you get is a classical output. So that's again important, that at the end, when you measure it out, every time you get a classical input. And every quantum algorithm is dependent on this clever process in which you start off with this entire big light blue like space of solutions. And with this clever process, you shrink it down to the dark blue solutions with a higher concentration. So when you sample out, when you measure it out, you make sure that the clever process takes care of that you sample out solutions from the small space more, and that's where your solutions lie. So how do computations look when you compare it with a classical computer? So if you have, let's say, a classical computer, for example, in the red one, you have something like a GPU, where for each of your inputs, you want to do the same thing. So if you are doing that and you want your results at the end, for example, you're doing something like matrix multiplication, you don't get a lot of interaction between these inputs, and it's not really useful to use quantum computing in these cases, because at the end you want to get every single output out of the system. So if you measure out, you get only one of these, then it's not useful doing this on a quantum computer. The nearest version of classical computer that comes very close to quantum computer is called as probabilistic computing. So in that, you have this probabilities associated with every single path of your calculation, and you interact them together. And finally, you want just one output, maybe the one with the highest probability in this case. The problem with probabilities is they range between zeros and ones. So at the best, you can reduce the probability down to a lower level, but it's very hard to make it to zero if you start with an equal superposition of probabilities. So that's where quantum computing comes very nicely, because now instead of probabilities, you have amplitudes, which are complex numbers. So they can be basically negative and positive. So when they interact with a negative one, interact with a positive one, exactly like how it happens in water waves, you can have destructive interference, so that you can reduce the final probability, which is like the square of these amplitudes, to a very low number. It can be as low as zero, so that the ones that you actually want to measure out, their probabilities increase by a much higher amount. So this is the inside trick of using quantum computing. If you have this kind of structure in your quantum algorithm, then it's going to give you an advantage. So coming to the second half of the talk, not half, I guess we are far after that. So for so long, we explored that what is the motivation of using and developing quantum computers. So that was, again, most of this work was done like from Feynman's time, from 1980s to Deutsch's time, when the quantum Turing machine was invented in the 1900s. And then 1990s again, sorry. And then we had some already good quantum algorithms like Shor's algorithm and Groover's algorithm already in the 1994 and 1996, I guess. So people already knew what to do with quantum computers, but nobody was bothered about making these devices. Because why? Because nobody actually had this push to make these devices, because classical computers were having a great time solving the problems for us. So that slowly came with the slowdown of what's called as Moore's law. And that is more like a trend that we see in the semiconductor industry, that the number of transistors that we are able to pack on a chip kind of doubles every 18 months. So this is, again, not a law like a mathematical law. This is like a trend of human engineering ingenuity, that every 18 months, people come up with smart ways of packing more and more transistors on a chip. And the more number of transistors we have on the chip, the more powerful that computer is, and we are able to do more and more things with those kind of computers. So this was the backbone of the industry that gave rise to like all the big computing giants like IBM, Google, Intel. So all this, like a huge part of our economy actually depends on that your laptop or your mobile will slow down. There will be a better model in the market 2 to 3 years from now, and you will like throw away your old laptop and phone and you will buy a new one. So a lot of economy actually depends on this fact of the Moore's law. And it was not only like algorithms, there was also a lot of development from the VLSI manufacturing side, which led to this continuing trend. But people were already seeing this slowdown. If you look at this graph, around 2005, people already started to see that the graph is kind of flattening. So that is mostly because of what's called as quantum tunneling and the technologies that people had to take care of to prevent quantum tunneling. So transistors are basically a barrier that stops the electrons from flowing from one side to the other. That is based on some potential difference that you create so that the electron cannot cross over. So when you're packing more and more, and that basically is the 0 and 1 switch that you need to run your Boolean functions. And now,
can you tell me how long this is going to be? Because
10 minutes, I guess.
Ah, cool, perfect. So then, sorry to interrupt. Thanks.
So yeah, coming back to the transistor. So once you try to pack up a lot of transistors on a very small area, you need to reduce this barrier as well. So now, due to the quantum effects, it can transition from one side. It can just go from one side to the other, just like we have in the quantum world. And to prevent that, we had to take care of other things like reducing frequencies, lowering the power, and all this kind of things. So eventually, we know that it will stop at some point of time, because we are going to reach the place where the barrier is just an atom thick, and then you cannot prevent things from going in the quantum direction. So we need to look at alternate technologies so that our progress of civilization keeps on going. And one of them is the quantum computer. So quantum accelerators are like the term that we use so that it's not going to take over all of your computing system. You're not going to play mostly your games on a quantum computer soon. It's going to remain on your GPU. So these accelerators are basically very specialized coprocessors, which takes care of very specific functions from your normal host CPU. So if you're playing a game, for example, and it requires a lot of graphics, the CPU gives away that part of your computation to a GPU. It does that computation and gives the CPU back. And that's also going to happen for quantum computers. It's not going to take care of everything. So how does a quantum accelerator look like? It has all the stack layers that I won't be going into today, but it's not so easy to make a quantum computer directly, because it has all these different layers, the same ones that we see even on a classical computer. But even while this technology is developing, you can also try out all of these on what's called as a quantum computer simulator. So that's like that kind of emulates the process that we would have, the same math. And you can try out your algorithms on a quantum simulator while this is being built up. While you are making the stack, one of the lowest layer that you need is the chip. And in this chip, you basically have the unit of quantum information, which is the qubits. So this is where the experimentalists come in. So they started the revolution of making qubits. So let's make qubits. The first thing that they encounter is a lot of errors. Because quantum states are super fragile. Every time they interact with the environment, even by a little, they collapse to, like, you cannot keep track of the computation that's going on. So normally they are isolated in huge dilution refrigerators and also this framework around it to take care of other environmental effects. So that's mostly what we use for quantum computing. We cool it down to a very low temperature, around 20 millikelvin or even lower. And that keeps the qubits isolated. But there's another factor that we need to take care of, and maybe only environmental isolation won't cut it, and that's quantum error correction. So where in quantum error correction, you take multiple qubits and distribute your quantum information over this qubit, so that if some part of it goes bad, like couples with the environment, then you still can make out part of your quantum information from the remaining qubits. You don't lose the entire computation. There are various codes available. Again, I won't go into that today. But the basic problem with it is to implement quantum error correction, you need more qubits. And unless you are in the quantum error correction threshold, having more qubits is just making your system even far worse. So we can plot this graph where you have the number of qubits and the error rate. So this is where we are right now in the red arrow. And this is where we want to be, which is called as a fault-tolerant quantum computing, the blue arrow. And even 5 years back, we were of the opinion that we can go directly, the systems are going to improve very rapidly, and we are going to directly go from the red arrow to the blue arrow. But slowly we are realizing that that might not be the case. It's not so easy to have this, to engineer these systems. So that's basically what is known as the NISQ era, the noisy intermediate scale era, where you reach a number of qubits which are still very difficult to simulate exhaustively on your classical computers. So that is pretty much the 50 qubit limit, because the number of states 2 to the power 50 is already too high to even use a supercomputer. But the qubits are still pretty noisy, and unless we actually experiment with it, we will never know whether it's going to work or not. So initially people were designing these quantum algorithms by themselves. And later on, right now, we use a much different strategy, which is popularly known as quantum software 2.0, where instead of writing the algorithms, we make a classical computer write the algorithm for us. We give it some kind of a format of what we want, exactly like the cat image or how we train a neural network, that we want to distinguish between cat and dogs. And then every time the classical computers is going to write the exact quantum circuit for us and tell us that this would work for distinguishing between cats and dogs. So this is the basic idea of the variational circuits. That is one of the most used quantum algorithms nowadays. So right now, if you look at the big picture, we have the hardware on the lower layers, and we have various softwares that people already are working on. And there is a huge gap between them. So the hardwares are right now trying to make 1 or 2 good logical qubits or a few noisy qubits, and trying to see whether they can implement a set of universal gates on it so that we can eventually run all of computation. Whereas if you look at the algorithms, the algorithm designers are using hundreds to 1,000 qubits to actually try to map a real world applications on that. So, and there's no way of executing them even on quantum simulators. So this gap will bridge, but maybe 10 years from now, like, it's hard to predict. But if you look at what work has been done so far, there was like one part of the work where, let's say the early Shor's and Groover's algorithm, where you have an algorithm and you have a proof that the algorithm will work. There is only development of a quantum processor where you just try to run an universal set of gates. And then we have the quantum supremacy experiment where still there's no application of that, but you have a proof that you have run something that is not possible to do on a classical computer. This is mostly what I work on, where I do not look at the quantum hardware, but I try to map this algorithm to a real world application and try to see how many qubits I would need to do that. And finally, one of the most popular ones is the variational algorithms, where there's not so easy proofs that it will work. Those are like heuristic based, but they can be kind of mapped to an application level and kind of can be run on a hybrid system, where some part is done by a classical computer and some part of the computation is done by a quantum computer. So if you look at this graph on the left, it can be kind of divided into 3 zones. So in the future, we have the fault tolerant quantum computing, where this software and hardware gap is fairly bridged. And this is the NISQ era right now, where most of the focus is what can we run on the noisy hardware. And my PhD professor and I, we are working on what's called as perfect intermediate scale quantum computing, where we are mostly looking at perfect qubits. So we are running on ideal systems so that when you're developing an algorithm, you don't get carried away by all the noise models and making things more difficult to design an algorithm. Yeah, so the last few slides. If you look at the practical limits now of quantum computing and classical computing, so there is this set of problems that can be solved by computers. So, and they happen to be the same. So quantum computers cannot actually calculate a function that you cannot do with classical computers. So they are, in the technical term, cannot do a super Turing computation. But what a quantum computer can do efficiently is higher. So they can do some problems more efficiently, which a classical computer cannot do. But right now, most of this computation is done by a classical computer, whereas quantum computers are starting out to do only a specialized type of computation. So looking into the future, like the type of problems where classical computers are good at, they're going to handle that, whereas all the other problems will be handled by other accelerators. So that would include both classical and quantum accelerators, whereas a very small part of that computation, which are really suited for quantum, those will be handled by the quantum accelerator. Also, are there any theoretical limits of quantum computing? Actually, there is. But like the assurance that we have is quantum computers are as good as computing gets with our current laws of physics. It is possible theoretically to make a quantum gravity computer, but like if you have watched the Interstellar movie, you can go around like near a black hole so that you get like space time gets deformed and you get a lot of time in that space-time region so that you can do a much more complicated function. You get a lot of time, so you can do a lot of computation around a black hole. But that would require you breaking some laws of physics. So quantum computer is kind of as good as computing gets. And people are actually researching on this quantum gravity kind of ideas. And Scott Aronson is a famous guy in complexity theory, quantum complexity theory. And he works a lot on these kind of computers where you can imagine, of course, much more complicated problems. So going towards the end of this talk, like you can stop at this and understand that we have come this far and we should be happy with what we already have right now, but physicists are kind of never happy. And you can always ask bigger and bigger questions. And John Archibald Wheeler is like famous for asking all these philosophical questions of like, why do we have quantum, or like what exactly is a bit? Can we model the entire universe just by flipping bits? And one of his ideas is maybe the universe is existing because we as observers are there to see it. And there's not only John Wheeler, even Einstein imagined that, is the moon still there if there's nobody to look at it? And in quantum mechanics, that kind of gets a bit difficult, because in quantum, we assume few things, exactly like the problem that we started out with David Hilbert, that there are these properties that quantum mechanics should have. It should be universal, it should be consistent, and both facts cannot be true. So quantum mechanics should apply to everything. Two agents should not contradict when they're measuring something out. And of course, a coin cannot be both heads and tails at the same time. And it turns out that maybe we cannot have all these three together. Maybe quantum computing is not consistent, and there can be predictions made by two different observers that do not agree. quantum mechanics has ways of making sure that these two observers never meet. Let's say one falls into a black hole and one stays outside. In that case, both these observers might see something very different, but they're not going to match their observations anytime soon. So that's kind of allowed by quantum computing. And that's mostly what I am currently researching on. So there's another concept from John Wheeler, where if you are starting off with the Big Bang, you cannot have a law that kind of predates the Big Bang, because that is the beginning of everything, right? So the Big Bang and the grand unified theory should have begun at the same moment, both the universe and the law that describes it. So you cannot say that the law, the grand unified theory, already existed before the Big Bang. So that was the idea. And sometime back, we saw that quantum mechanics has this postulates, the 6 postulates by which you can explain everything. People are also trying to formulate quantum mechanics with much lower number of postulates. And one of this work focuses on just deriving all of quantum mechanics with just one postulate. And that's what is the most probable thing that we are going to see, given that we already had a set of observations. So in this example, we have the series of zeros and ones. And you can understand that we will most likely see a 0, 1 in the blue part, because that's the shortest, basically the code that we can write to generate it. So that's basically the idea that I'm working on, but that's for some other time that I can explain to you the idea of quantum reinforcement learning and how we can use that to derive the basic rules of quantum mechanics and what we are going to see in a quantum experiments. And this is what I am working on, a reinforcement learning agent, which can kind of start off with a very simple law of quantum mechanics and evolve, so that maybe you reach something like Newtonian physics and then you reach relativity. Newtonian physics is simple. You can still apply it with some assumptions, but Einsteinian mechanics is more complete, so you can apply it to more stuff. So that's basically what I'm working on. Going back to the imagery of the cave. So let's put things on this image. So the bird that you see on the left side, that's like the actual law that's governing the universe. That's something like the law, the quantum gravity, the grand unified theory. But the projection that you see of the quantum gravity is normally always classical. So that's all that we as human beings can sense it. And every construction of our theory should be based on this classical mechanics that we see. And we should be able to derive all of quantum mechanics just by looking at this classical world. There's just one small last catch to it, except that I'm not trying to describe another human being what this quantum mechanics is, but I'm trying to do it on a robot, so that the robot or the intelligent agent can derive the laws of quantum mechanics from this classical observations. Yeah, that's the end of my talk. Thank you.